Okay, now it's time to solve the problem. So I'm going to erase all this. Hopefully you have all this written down. Let's draw a picture of what's happening and try to analyze where we're going to start on this thing. So the situation is you have a ball going in a vertical circle, so it's spinning like this. Okay, you can have it spinning either way, it doesn't matter. And as it's spinning around, we have certain things. We have the length of the string here. It's a 60 centimeter string. I'm just going to convert that and make that 0.60 meters. Okay, we also know that this string, the center here, is at 2 meters above the ground, 200 centimeters. Okay? The spring breaks, and the spring breaks at this point over here, so that the ball is moving in an upward, has an upward velocity. We know the ball then will continue in a straight line because there's no centripetal acceleration on it after the string is broken, and it goes up till it reaches the height of 6 meters from the floor, from our platform down here. All right, and what we're trying to find is what we really want to know is what the tension is in the string is right at this point before it breaks. So what we need to do is draw our free body diagram. So at this point right here, here's our ball. We have gravity working this way, and we have tension going this way. Those are the only two forces acting on the ball at that point. So we can say that the F net x direction is equal to minus t, or minus the tension. Okay? But we know it's going in a circular motion, and that the center of the centripetal acceleration is towards the center, so we can put in this is minus v squared over r is equal to negative t. Okay? And then, notice that we can multiply by -1, and the negatives go away, so you can just say t is equal to mv squared over r. Well, we already have the mass of it, we have the radius, okay, and we have the mass, so all we need to do is figure out what the velocity is. If we figure out the velocity, we can get the tension of the string. So to figure out the velocity, we have to use our projectile motion equations, because we know once it releases this point, it is just a projectile. The only thing acting on it is gravity at this point. And we know how high up it goes, so we can use this equation, minus 2g y minus y naught, and solve it for the initial velocity at this point. So this is where the initial velocity is. The final velocity up here is going to be equal to 0 when it gets to the highest point. So we can put that in, and we can solve this. So we're going to solve this for v, which is just the square root, we're solving it for v naught. We know what v is, that's going to be 0. So we're going to say v naught is equal to the square root of 2g y minus y naught. Okay, so we have all that. We're going to say v naught is equal to the square root of 2 times 9.8 times the y final position is 6. The y initial position is 2. And if you solve that, you get that the initial velocity is equal to 8.85 meters per second squared. And then we plug that back into t to solve for tension. So we solve for the tension. We get that the tension is equal to the mass, which was 0.1 kilograms, times the velocity, 8.85 squared, all divided by the radius, 0.6. You get the tension in the string is 13 newtons. That is how you solve that problem. But I don't want to stop there, because we can do another thing. What I want to know is at this point right here, right before it's released, what is the total acceleration on that ball? So we want to know the combination of the centripetal acceleration right before the string breaks, and we have gravitational acceleration, g, in this direction. So our total acceleration is actually going to be a combination of those two. So our second part of this, which is not in the book, but I want you to solve anyway, is find the total acceleration on the ball just before the spring breaks. String, sorry, not spring. All right, notice that the centripetal acceleration is always aiming towards the direction of the curve, always perpendicular to the velocity vector. This is the velocity vector going upward. In this case, gravity, because it's going in a vertical circle, gravity's down, and so our total acceleration is going to be a combination like this. Those are perpendicular to each other, so we have to use the Pythagorean theorem to figure this out. Well, this is very easy because we know centripetal acceleration is going to be v squared over r. And we know v already. V is equal to 8.85, so it's just 8.85 squared divided by the radius of 0.1, which gives a centripetal acceleration of 130 meters per second squared. And we know that gravity, g, is just 9.8 meters per second squared. So the total acceleration is just the square root of 130 squared plus 9.8 squared. Take the square root of that, and you get that it is 131 meters per second squared. And then we also want to know what direction that is. Okay? So we have the centripetal acceleration going this way, and if I drew this better to scale, notice this is about 14 times that. So you're feeling 14 times more acceleration from the string, the ball is, than it is from gravity. So this should be drawn like this. And then our total is going to be this one out here. So what I want to find out is this angle right here. Remember, g is just a vector. We can move that vector out here, and now I got my right triangle, and I can say that theta is just going to be equal to, this is the centripetal acceleration, it's going to be the inverse tangent of g over a centripetal, or theta is just going to be the inverse tangent of 9.8 over 130. And I get my angle is equal to 4.3 degrees below the horizontal. And that's how you would solve that. So the answer is going to be this and this. And our tension is 13 newtons.